If a wire carrying a current goes through a magnetic field, why does it move? This is the actual force law for magnetism, and it's different to what we saw in electric fields. So first is the concept. A magnetic field doesn't pull on a wire like gravity. It pushes sideways or at right angles or perpendicular to both the direction of the current and the direction of the magnetic field. This means the force is zero if the wire is aligned with the field and maximum if the wire is perpendicular to it. We're going to see this when the math comes up soon, but here's a little visual for you. Imagine you have a horseshoe magnet like this. You've got your poles and there's a field in between. They will be. They go left to right. If you run a current through a wire, through it like that, it's going straight through. I couldn't show you going straight through because we're on a 2D page here, but try and imagine it. If you run the current along like this, the wire jumps up. And if you reverse the current, then the wire goes down. What's happening? The magnetic field is trying to twist or push the wire sideways. And this direction comes from a specific tool called the right-hand rule, which I introduced to you in the previous video. But a quick recap, point your fingers in the direction of the current and then bend your fingers in the direction of the magnetic field, right? You kind of close your hand, that kind of motion. And then wherever your thumb is, it points in the direction of the force. So if your thumb is going up, the force is going this way. If it's a negative charge like an electron, then the force is the opposite direction, so down. Here's some math. Here's the formula. And this and every other formula you ever need is on the free cheat sheet in the description. It's the force is equal to the current times the length of the wire going through the field times B, which is the strength of the magnetic field, just like how E is the strength of an electric field, multiplied by sine of the angle between the current and the field. That was a lot. Let's go through an example. If a wire carrying 25 amps of current goes through a 0.2 strength field and it's 0.12 meters long, angled at 60 degrees, then the force happening is 25, which is the current, times the length, 0.12, times the field, 0.2, times sine of the angle, sine 60. This gives you an answer of 0.52 newtons. This is a real force. This is enough to push a wire out of position in things like motors or speakers. How about the magnetic force on a particle? What if the wire disappeared and you zoom in on the moving charge, let's say a proton or electron? The magnetic field still pushes it. It's the same rule. However, the formula has changed. It's force equals the charge times the velocity of your thing times the field times sine of the angle between the velocity and the magnetic field. Right-hand rule works for this as well. Example problem time. Imagine you have a moving proton and it's inside of a uniform magnetic field. We're trying to find the magnetic force on this moving proton. So let's say the speed it's moving at is 4 times 10 to the power 6 meters per second. And the magnetic field, B, is equal to 0.3 Tesla. That's the unit that we measure strength of field in. The charge of a proton is known as positive 1.6 times 10 negative 19 coulombs. This is the same as an electron, but it's positive instead. And the angle is 90 degrees, which is perpendicular to the field. And so we use the force formula, which we just looked at, and it's on the cheat sheet in the description. It's here. Since the angle is 90 degrees, sine of 90 degrees is equal to 1. So we don't have to consider that. It's at its maximum force here. Force is equal to charge of our thing times speed, which is here, times magnetic field strength, which is 0.3, giving us force as 1.92 times 10 to the power of negative 13 newtons of force. It's less than a billionth of a newton. But for a tiny, tiny mass like a proton, this is enough to cause tight circular motion. And what's a Tesla? This Tesla is the SI unit of the magnetic field strength. 1 Tesla is equal to 1 Newton divided by 1 Coulomb per meters per second. It's the global SI systems unit for a magnetic field strength. So you can use it alongside kilograms and seconds and meters. So because the magnetic force is perpendicular to the velocity, it doesn't slow down the particle. It just bends it. If you remember centripetal acceleration, the reason why things move in a circle is because there's always a force pulling it toward the center. This is just like what a magnetic force does to your velocity. It's not pushing against, it's not supporting it. So the speed doesn't change. It just bends it, which creates circular motion. And we have a formula for this, which is also on the free cheat sheet. R equals mass, velocity, charge, magnetic field. And this is how mass spectrometers work. This is how mass spectrometers work and how Earth's field bends solar particles away from us. Let's go through an example. Say you have an electron and it's moving at 2 times 10 to the power 7 meters per second inside of a magnetic field of 0.025 teslas. Then what's the radius of its path? It's given by this formula, which we just looked at. Radius equals mass, velocity over charge field. What's the mass? Mass of an electron is 9.1 times 10, negative 31. And what's the velocity? It's the problem setup. So 2 times 10, 7. Divided by charge of an electron, as you know, it's 1.6 times 10 to the power of negative 19 times the magnetic field strength, so 0.025. This is 4.55 times 10 negative 2 meters. This is about 4.5 centimeters. This is what the magnetic field is doing to our electron. Here's a bonus fun little thing, it's helical paths. So if your particle has a component of velocity that is parallel to the field, then it's going to spiral along it. It's not just going to orbit in a flat circle. This is what happens in Earth's magnetic field, especially near the poles. I thought this was a cool little fun fact.